Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is series AC circuit analysis. Our objective is to introduce fundamental series AC circuit properties and examine series AC circuit analysis techniques like Kirchhoff's voltage law. Additionally, we'll examine the influence of shorts and opens inside series AC circuits. Bottom line up front, series AC circuit analysis is series DC circuit analysis using phasors. I cannot make it much simpler than that. This lecture therefore operates under the presumption the viewer is intimately familiar with fundamental series DC circuit properties as illustrated in the Basic Electronics 1 DC Circuit Analysis playlist available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. Additionally, it is presumed the viewer has ample experience with complex numbers, phasor representation of AC quantities, and Ohm's law as it pertains to AC circuit analysis. If there is the slightest hesitancy on your part regarding any of these topics, go away and do not come back until you have mastered these subjects. If you feel you are among the worthy, let us begin. Let's explore basic series AC circuit properties in terms of impedance, current, and voltage distribution. Let's first examine impedance inside series AC circuits. As you are no doubt aware, the complex impedance of a series or inline configuration of elements is the summation of those impedances comprising the series relationship. Consider a series combination of three elements. The first element is a 120 ohm resistor. The second element is an ideal 250 millihenry inductor. And finally, the third element is a 47 microfarad capacitor. The sinusoidal AC voltage source has an effective value of 120 volts and an excitation frequency of 60 Hz. The complex impedance of the 120 ohm resistor is 120 ohms at an angle of 0 degrees. Let's call this impedance Z1. Illustrated in a plot of complex impedance, Z1 has a magnitude of 120 ohms and is pointed entirely in the horizontal positive real direction. The complex impedance of the reactive inductor and capacitor necessitate a bit more computational effort. The complex impedance of the 250 millihenry inductor at an excitation frequency of 60 Hz is roughly 94.2 ohms at an angle of 90 degrees. Let's call this impedance Z2. Illustrated on a plot of complex impedance, Z2 has a magnitude of 94.2 ohms and is pointed entirely in the vertical positive imaginary direction. The complex impedance of the 47 microfarad capacitor at an excitation frequency of 60 Hz is roughly 56.4 ohms at an angle of negative 90 degrees. Let's call this impedance Z3. Illustrated on a plot of complex impedance, Z3 has a magnitude of 56.4 ohms, only it's pointed entirely in the vertical negative imaginary direction. The AC voltage source sees a total impedance equal to the summation of these three series elements. Total impedance ZT equals Z1 plus Z2 plus Z3. Substituting in our given values yields a total impedance of 125.8 ohms at an angle of 17.5 degrees. If you wanted to, you could calculate or express this using rectangular format as 120 plus J 37.8. You note the inductor and capacitor point in opposite directions on the vertical imaginary axis and serve to moderate each other's influence, such that the source is under the impression that the total impedance has a somewhat inductive nature. As a result, the complete series circuit should exhibit slightly inductive behavior. Let's put these impedance values aside and examine current in series AC circuit. As you are no doubt aware, a single path for current exists in the series circuit. As such, current through element in series is the same. This is the most fundamental series AC circuit property. Any current leaving the source must travel into resistive impedance Z1. Any current leaving resistive impedance Z1 must travel through inductive impedance Z2. Any current leaving inductive impedance Z2 must travel through capacitive impedance Z3. And any current leaving capacitive impedance Z3 must return to the source. Source current IS equals I1 equals I2, which equals I3. If we solve for source current or current through any single element within this series circuit, we by extension solve for current through all remaining elements. I say again, current through elements in series AC circuits is the same. This is the most fundamental series AC circuit property. Ohm's law states that source current will be equal to supply voltage over total impedance. Substituting in our given values yields source current to be approximately 953.8 milliamperes at an angle of negative 17.5 degrees. The phasor diagram illustrates that source current will lag supply voltage by 17.5 degrees. This small amount of lag is to be anticipated given the somewhat inductive nature of our total impedance. Before moving on, it may be helpful to remind ourselves what phasors represent. Recall that phasors are simply shorthand representations of more complex time-variant sinusoidal phenomenon conveying the most pertinent information, notably RMS or effective value, and the degree of phase shift in a compact and convenient format for the purposes of calculation and algebraic manipulation. If we represented supply voltage and source current as time-variant phenomenon, they would look something like this. Supply voltage with an effective value of 120 volts would peak at roughly 170 volts. A waveform with a frequency of 60 Hz would sinusoidally alternate over a period of 16.7 milliseconds. Source current with an effective value of 953.8 milliamperes would peak at roughly 1.3 amps. Source current also sinusoidally alternates every 16.7 milliseconds. Source current would appear to lag supply voltage by roughly 810.2 microseconds, the equivalent of 17.5 degrees. All elements in this series circuit would experience the same time-variant sinusoidal current. Given our combined impedance is in fact the series combination of Z1, Z2, and Z3, it can be said that I1, I2, and I3 also equal 953.8 milliamperes at an angle of negative 17.5 degrees. Let's now examine voltage across each individual element within this series AC circuit. Ohm's law states that voltage is current times impedance. Given each element in the series circuit experiences the same current, the voltage drop across an individual element will therefore be proportional to an individual element's impedance. An application of Ohm's law for resistive impedance Z1 demonstrates V1 to be 114.5 volts at an angle of negative 17.5 degrees. The phasor diagram demonstrates the current through the purely resistive impedance Z1 will be in phase with the voltage across it. If we were to add a plot of voltage across resistive impedance Z1 as a function of time, it would look something like this. Note V1 in orange is in phase with the current through it. V1 appears to lag our supply voltage by 17.5 degrees. An application of Ohm's law for inductive impedance element Z2 demonstrates V2 to be approximately 89.9 volts at an angle of positive 72.5 degrees. The phasor diagram demonstrates current through inductive impedance Z2 would lag the voltage across it by a relative 90 degrees. If we were to add a plot of voltage across inductive impedance Z2 as a function of time, it would look something like this. V2 in yellow appears to lead supply voltage by 72.5 degrees. Note current through Z2 appears to lag voltage across it by 72.5 plus 17.5, or a relative 90 degrees. Finally, an application of Ohm's law for capacitive impedance element Z3 demonstrates V3 to be approximately 53.8 volts at an angle of negative 107.5 degrees. Phasor diagram illustrates that the current through capacitive impedance Z3 would lead the voltage across it by a relative 90 degrees. If we were to add a plot of voltage across capacitive impedance Z3 as a function of time, it would look something like this. V3 in green appears to lag supply voltage by 107.5 degrees. Note current through Z3 appears to lead voltage across it by 107.5 minus 17.5, or a relative 90 degrees. It's moments like these which truly convey the utility of phasor diagrams. Yes, one could take the time to painstakingly plot and interpret all these electrical properties as a function of time. However, phasor diagrams convey the same information from the smallest possible space in a far more readable fashion. Allow me to highlight some important properties regarding voltage distribution within the series circuit. You'll note that voltage drops expressed as phasor equivalents have both a magnitude and a direction. Consider the range of voltage magnitudes first. You'll note the impedance with the largest magnitude in this series relationship, in this case, impedance Z1, experiences the largest voltage magnitude of 114.5 volts. Additionally, you'll note the impedance with the smallest magnitude in this series relationship. In this case, capacitive impedance E3 experiences the smallest voltage magnitude of 53.8 volts. Let's now consider the range of voltage phase shifts exhibited by these individual elements. The voltage drop across purely resistive impedance Z1 is perfectly in phase with the current through it. In contrast, note the current through purely inductive and purely capacitive impedances Z2 and Z3 respectively lag or lead the voltage across them by a relative 90 degrees. Given there is a 90 plus 90 degree phase shift between these two reactive elements, it can be said that voltage drops across the purely inductive and purely capacitive impedances Z2 and Z3 are completely out of phase with one another, or shifted by a relative plus or minus 180 degrees. Inductors and capacitors appear to have opposite natures. When one peaks, the other valleys, and vice versa. Finally, let's consider the combined effects of both magnitude and direction. You'll note the summation of individual voltage drops, V1 plus V2 plus V3, taking into account both magnitude and direction, equals the total voltage rise of 120 volts at an angle of 0 degrees. This should not be a surprise because of our previous experience with Kirchhoff's voltage law. Recall that Kirchhoff's voltage law states that the summation of voltage rises equals the summation of voltage drops. For this series circuit, comprised of 3 elements and a single voltage source, the Kirchhoff's voltage law equation would be E equals V1 plus V2 plus V3. What goes up must come down. This is again where it's very helpful to remind ourselves what phasors represent. If we used our plot of electrical properties as a function of time, at any instant in time, the summation of instantaneous voltage drops V1 plus V2 plus V3 do in fact equal the instantaneous voltage rise induced by the source. Consider a moment in time a quarter of the way through the cycle, at roughly 4.2 milliseconds, when the source peaks at an instantaneous value of 169.7 volts. At this same moment in time, V1 in orange has an instantaneous value of 154.4 volts. V2 in yellow has an instantaneous value of 38.2 volts, and V3 in green has an instantaneous value of negative 22.9 volts. The summation of these instantaneous values for the individual voltage drops do in fact equal our voltage rise of 169.7 volts. Other instants in time would yield similar results.